Daniel presentation will begin shortly. The presentation time is 30 minutes. Please welcome Daniel with huge round of applause.
Hello, everybody. So my name is Daniel. It's great to be here. And thank you for coming. And thank you for listening to me speaking at stuff that's not my main area of expertise. Because you'll see, I am a software engineer. I'm currently working at Bloomberg. My job is in education. I train other engineers there. And you can also find me in social media, typically in Reddit or YouTube, and a few others at those links. I'm telling a story today about a project that's not job-related, because it's building hardware. I'm definitely not an electrical engineer. So my goal here is not to teach you how to do something specific and go over the details, but more to inspire you to have fun and make you want to build things. But my story starts with work. So I was researching how to create educational videos with technical information, and I found a YouTube channel from a person called Ben Eater, who built this. And what you're looking at is an 8-bit homebrew CPU made out of very simple parts and breadboards and lots of wires. And he describes this over a very educational series of videos, which is amazingly made. So besides my interest on the educational bit, I have always been kind of curious to explore more electronics, and this looked super fun. So amazing, I have an excuse to jump in, right? And it was my turn to build something. So what you can see here is kind of my own twist on an 8-bit CPU that I actually brought with myself. And I can showcase this in the open spaces if I'll probably be around. My build has a similar architecture, built with somewhat different tools and components. So the picture is a partially completed version. And the story begins actually way back, both for me and for Ben, because it starts in the 1970s with this book that describes an 8-bit computer that could be built even with 1970s parts. So very, very simple and available components even today. And even if this is very, very old, almost 50 years, most of the concepts about computer architecture that I find here still apply today, perhaps in some more evolved versions. But the computer described here is for educational purposes. It's not a great computer. Let me show you some specs. So this is an 8-bit computer, right? It operates on 1 byte at a time, and it can do arithmetic, addition and subtraction. Don't ask it for much more. And it has the amazing storage capability of 16 bytes of RAM, not megabytes, it's bytes that you can count memory addresses with your fingers and a few toes. And it has 11 different instructions that run at blazing 400 hertz. Actually, it could run much faster even with 70s hardware. It's intentionally designed to be slow because you want to learn and observe what it's doing. And so the slowness is actually a feature. So I run this at actually hundreds of megahertz, but it's fun when you see it doing things slowly. So let's see what we can use to build this design, which is called the SAP1, the simple as possible computer. So the versions that that you saw before actually are a bit of an extension of the SAP1 in the book to make it more interesting, but with almost the same hardware. What can we use to build it? And there's some people doing homebrew CPUs out of bare transistors, super hardcore, and great if you do learn about semiconductors and calculation of circuits, more on the analog side. But I was more interested in digital logic, so it's not the right abstraction. And what the book proposes and what the first Breadboard computer in the videos use is this logic integrated circuits that have very simple abstractions like logical functions and or not, registers, which are essentially like a variable, or other, which adds two 4-bit numbers together. And out of those you can build anything. And in terms of circuits, of course, as time evolved, engineers started creating more higher level and complicated circuits that have more functionality. To the point that in modern 9, and actually not much further than that, you could put an entire computer in a single chip, which is what we normally do, perhaps even in entire system. So going higher level is always kind of a trade-off. It's always more convenient, same as in software, and at the same time, you lose some control over the design. So for these CPUs, I cannot control, or my controllers, you cannot control what kind of instructions runs, how it runs. You can write software for it, but writing software is my show, so I want to do this as a hobby. So it's still super fun, but not what I wanted to learn. And something about this is that the abstraction, the power of this is so great that they kind of eaten up the middle points of the abstraction layer. So today you can either get this or very low-level components, but it's hard to get stuff in the middle to do logical operations. So what are my options? I could do like Ben and build kind of out of individual chips. But this is where I took a different turn and decided to explore something a bit different. So what you see here is a field programmable gate array, which is a square chip in the center of the picture, inside the board. For scale purposes, the connector on the left is USB-C. So this is actually quite small. But these chips essentially contain a lot of internal logic blocks, which you can consider as those individual logic chips that you could buy separately. And there's an interconnection network in the middle that you can configure. So you plug into USB-C, you kind of rewire it internally, and then it remembers that configuration, and you have a custom circuit. So you get the flexibility of kind of building something on your own with the convenience of having a small object and controlling everything from your computer, so more convenient. And FPGAs used to be rare and expensive, but this board actually you can get between 20 and 40 US dollars. So it's quite affordable, more expensive than a microcontroller, but not too much. So that means that I have decided what's my platform. Now I need to decide, okay, what's the kind of, how do I describe a design? And again, I came from the world of software, probably most of you do in this conference. People on the hardware world, we share some things. For example, we share block diagrams. Block diagrams, you describe a system kind of like the large components and which is connected to one another. And this is actually from the computer you saw. But what you get here is a very top-level view. This doesn't have enough detail for implementation. There's some inner details that are kind of intentionally hidden here. So if you look, for example, at the book, you get some schematics, or for Ben's version on the right. And schematics are super detailed. If you know how to follow one of these, even without understanding how it works, you implement it and it should work. But again, they're kind of low level. So for example, in the right, you see the arithmetic unit for the computer, and the yellow blocks on the vertical yellow blocks are 4-bit adders. So I need 2 because it's an 8-bit computer. If I want to say, oh, I want a 16-bit one, I need to add 2 more and add a lot of interconnections, which follow the same pattern, but it's kind of repetitive, and I need to do the same. And if it's 64-bit, even more. So it's not capturing the main concept. It's capturing perhaps too much detail. It doesn't have enough abstractions for repetitive bits, so I need to repeat when something happens multiple times. So I would like to be able to describe a design with the flexibility I'm able to describe software. And there are tools to do that, which are hardware description languages. So a hardware description language is something that you write with your text editor, similar to code, and they have a syntax that you have to learn, and they have abstraction constructs to avoid repetition. But at the same time, it's for hardware. It describes a physical object with, in the end, a limited amount of resources. It's not like a program that you can make it abstractly grow based on available memory. A main difference is that you're describing hardware which works with a different logic. In software, you normally work sequentially. You can do some things to make it concurrent. In hardware, all of the components are working at the same time. So by default, it's like every line of code in your program is running at the same time unless you stop it somehow. So you need to think about in a different way. And these languages are very widely used in the industry, not just to communicate designs, but also for synthesis, which is essentially translating a design into something you can put on hardware, like an FPGA configuration, or also they're used to actually create the kind of the patterns to create real ICs. But you can also, without any hardware, simulate those descriptions to check the behavior and test and verify how things work. So it's a language. It's not a programming language. It's a hardware description language. And what you will see in the industry is that everybody uses mainly two very popular HDLs, which are Verilog or VHDL, which are quite old. They come from the 80s. Of course, they are getting updated. And they were designed to describe hardware. They do this very well because that's their main goal. And that's why they are popular. As the industry evolved and people started doing more simulation, verification, variants on designs, users of these languages started to want more kind of programming language features. Even if it's stuff that you can do in a programming language and cannot directly translate into hardware, synthesize. Sometimes you may want to write kind of something like a test, and you write a component that interacts with yours in your simulation. And rather than describe that extra component hardware, writing as a small program is easier. So you may want to do that. And well, the programming features on these languages look a bit kind of like tacked on top of that. So they're not as good. They're evolving and improving, but with these influences from the software industry, many people started creating alternate HDLs that incorporate more modern programming approaches, so the software part. And I want to highlight today Amaranth, which is a Python-based hardware description language. And I say Python-based, actually, the programming part is just Python. You run the regular Python interpreter. And the hardware description bits are a library that you pip install and then import like any other library. It works with existing Verilog tooling because it can translate to stuff that they understand. And it's fully open source, and you can use it to wholly open source tooling, which I really like. So it's quite powerful. Just to make this clear, this is not write Python code and you get a circuit that does the same thing as your Python code logic. You write Python code that produces a circuit description. That's how HDLs work. So let's see what some of these examples, some examples of code written Amaranth with this HDL. And let's say, for example, I want to write the arithmetic component, right? It needs to be able to add and subtract two values. So this looks like a lot of code, but actually the core logic is the 4 lines kind of near the bottom, and the rest is kind of definitions and imports and boilerplate. So going slowly, I'm defining a component because I can define a component so I can reuse it multiple times. And it has certain inputs and outputs. This has 2 inputs, A and B, which are the values that I'm adding, and they are 8 bits wide. And a subtraction indicator that tells me, oh, I can, what operation I want to do. And it has an output value, which is the result. So this is the signature of my component. And I have some boilerplate where I need to always have this method that produces one of these module objects. And the module object is essentially what stores the design, the logic that the hardware needs to implement. So anything that I want the hardware to do needs to be kind of stored within my module. And the stuff that I can store within my module are, for example, these assignments. So this .eq, this library function, is not a Python assignment, because Python assignments run when I run my Python code, not when my chip is running later on. So this .eq essentially means generate the logic for assigning the computation on the right, like the addition or subtraction on NAB, into the value on the left, self.result. And I need to put those assignments in the module. So I put this in this attribute of the module, which is would call the combinational domain. These are essentially stuff that will happen with no synchronization all the time, unless something disables them. And I actually need to disable some of them because I cannot put the addition and subtraction at the same time. I need to control which one is done through this self.subtract input. And you have this kind of if-else logic to choose that and to control which assignments will be active at a given point in time. And notice again, this is not a Python if-else statement. An if-else statement will allow me to make a choice at the point where I'm doing the design. This m.if and m.else is the module m has the power of making decisions as it's running based on this to enable one or the other. So as you can see, yeah, the main logic is that for fourth line that says if I'm subtractive, the result is a minus b. If otherwise, it's a plus b. So very simple components in this computer. The other stuff I can show you is, okay, my computer needs some sort of memory, right? And I could describe logically how a memory works, and that'll be a lot of code. But rather than that, I can use libraries. So Amaranth has a standard library, and there are other libraries that you can get. So I can say, okay, I want to import a memory and use it in my RAM component that defines a few extra things around the memory. And you can put that memory as a submodule of the module I'm defining. So you can define these hierarchies of modules to reflect your top-level design. And once you have your submodule, you can kind of connect the inputs of your module, again, a lot of these .eq assignments, to the inputs that you have and tie everything together. So this is how you glue different components. And let me show you a different thing that you can create. So for this computer, I need a program counter, essentially a register that keeps track of which instruction I'm currently executing. I'm executing instruction 1, then 2, then 3. So it needs to be able to store a value and increase it by 1. Just for this demo, I want to say, OK, what happens if I don't want to hard code the size of the program counter? Well, this is Python code. So rather than putting constants, you can define a custom constructor that takes an argument, which is a width. And I define on the fly, while I'm building the design, what's the size of the signals that go in and out. So this is parametric now, and I can even have multiple counters of different sizes at the same time. Other than that, the logic at the bottom is actually kind of the same, no matter what's the width, because Amaranth figure out everything else. So I have these definitions of the width, and something different about the counter is that, well, if I turn on the increment signal that says, hey, you should count up, well, things are happening normally at the same time in circuits. So if I turn this up, this will start racing up at an arbitrary speed. I need to kind of be able to control this with something called a clock that essentially allows things inside the circuit to take turns. So by putting things into sync rather than comp, I make this synchronous and say, OK, this will increase once per each clock, so I can control actually how much it increments without having to worry about real time. So with these kind of components, you can actually build a computer. So let me describe you again how this is put together. So the white boxes are essentially registers. They are variables, either 8 or 4 bits wide. And the dotted line on the right holds the memory. I have the blue RAM on the bottom. This is like an array of 16 bytes. There's not much magic, no more magic than that. As any array, you need an index to access it. So the register that says memory address is kind of the index into that array. So at the bottom center, you have the arithmetic logic unit. We already saw that. It's two variables, A and B, a component that either adds or subtracts them together, and a few extra things that I didn't show to check if the result was 0 or if there was an overflow, which is useful for conditional operations later on. And an important part which I didn't show is that gray bar in the center, which says bus, because components are not, except for a few black arrows, they're not very connected to one another. Everything can either write to the bus with a green arrow, essentially place the value they have into the bus, or read from the bus. These are the red arrows. The red arrows essentially modify the content of one of the components. And of course, the bus can hold only one value at a single time. So something needs to turn on and off the green and red arrows at the right time to move data between components when I need that. And that's what the controller sequencer will do. So the control sequencer also controls the program counter, which is a counter I mentioned before, and when it should increase, and controls all of the bus signals in and out. And it has this instruction register, which is kind of like a temporary variable where I copy which instructions I'm executing right now. Not the address, which is a program counter, but the actual instruction. And based on the actual instructions and some other logic, it decides which other components to turn on at this time to work like a CPU. So this looks super complicated, but it's not much. I want to show you a few of these components, again, how Python benefits there. So for example, for the bus, well, a bus is a value and a selector of which is the input which is active right now. And I could write it like this, right? Like a case with multiple options saying if the selection is 0, data comes from A. If it's 1, it comes from the instruction. If it's 2, it came from the program counter, and so on. But rather than that, this is OK if I know the final design. But when I'm playing and tweaking the design, this is a lot of copy and paste code that I would like to be nicer. So I could say, OK, I could actually define a bus constructor where I define what are the inputs now and outputs as a regular Python dictionary. And on a loop on that dictionary, which you can see at the top, I can generate the different cases. So you can see now I have a for statement. This is a Python for statement, so that runs at the design preparation stage. And the cases are being generated, so the circuit will be able to manage all of the cases that this dictionary describes. So now you can see how this programming and design description work together. So you can programmatically do things. OK. The other thing that we need to describe is a bit more about the control unit. So I have this instruction register, which is actually 8 bits split in 2 halves. The first half is a number that specifies which is the instruction I'm choosing right now. Actually, there are 11 of them. And the second half is some sort of argument. So if I have the instructions, add the value in memory location 7 to register A, the first half will be an instruction called add, which adds a memory location to A. And the second half will be the number 7. And based on this, the control unit essentially has several kind of if statements that decide which parts to enable on the rest of the machine. And the machine at each turn of the clock can run what's called a micro instruction, which can move data through the bus from one place to another, but only one thing because there's only one bus, and decide what arithmetic operation to do, and increase the program counter, and a few other things. All of this actually can happen at the same time in a single micro instruction. But still, for most useful instructions, I need multiple of them. So I add something called a micro sequencer, which is essentially a counter that goes from 0 to 4 and loops, which essentially gives me 5 different steps where I can do different different actions at each one of these steps for each instruction. So I divide each instruction into up to 5 possible steps. And for example, the add memory 7. On step 3, I set the index of the memory from the operand in instruction. And then in step 4, I move data from the memory into register B. And in step 5, I ask the ALU, the arithmetic logical unit, to put the result of the addition back into A. So I started on step 3 because step 1 and 2 are required for every instruction to actually load the instruction from memory, which is something that every instruction needs to do at the beginning. So again, I could do a lot of if statements to do this, but I also can do, and there's no Amaranth in here. These are just some dictionaries and lists and some custom data classes I made up, where I can define the architecture of my CPU and say, these are the instructions I want, and these are the steps. And if I want a different CPU with different instructions and different sequences of steps, I just change this data. And there's some logic that, based on this, again, generates all of the statements and cases that I want to do. So this allows me to experiment and try different architectures. So again, that's when things like Python make you more powerful. So with that, you can define a few useful instructions and make something like this multiplication program, which you have the pseudocode on the left and some assembly on the right, and the column kind of in the center is actually the bit patterns that are stored in memory. And I can multiply 3 times 14, which is the data stored at the bottom. Memory is called X and Y, actually the last 2 locations in memory. And I won't go into detail on this. I can show you essentially you can get this program on the computer and start to run it. And you will see, once it starts running, that there's this vertical blue bar on the left. That's the sequencer following over each one of its 5 steps. So each loop of this blue thing is an instruction. And you can see the whole memory and the registers and what everything is doing. There's some color coding that I added on this display. So essentially, components in green are reading, sending the data to the bus. Components on red are being written to, so are getting data from the bus to modify the content. So you can see this operating and adding values sequentially on the output on the left, which is represented by a number. So eventually, this will tell me that 3 times 14 is 42. That's the correct answer. And that's custom CPU running. And I have a repo with this. There's a kind of simplified version, which uses like 150 lines of Amaranth code. It's not a lot. And they have a more elaborate one with more components and a little bit more organized. So that's what I want to show you and excite you about trying this and exploring this. So I just wanted to thank both the people who made Amaranth, which is a great tool. It's actually being used in the industry, and Ben for inspiring videos. And if we have time, I'm happy to take questions. This is the repo with everything and the QR. And if not, is the time for questions?
Yeah, thank you so much for your presentations. So if anyone has any questions, please raise your hands.
Thank you for the speech. It's truly fascinating to be able to take a look into how CPU works from a Python perspective. I'm not very familiar with hardware, so I'm curious about, you mentioned that it's easy to configure the custom GPT. And could you share a little bit about some example when you see it's not working as you expected and how you troubleshoot? Is it from the physics, like the signal panel, or you are more like troubleshooting it from the Python coding?
So I don't have it in a slide, so I can demo that later. But essentially, for some things, I actually can look at the panel, because in this case, I designed the CPU so I can observe the whole internal state with LEDs, because that's nicer and shiny. Normal CPUs don't do that. So this is very easy to introspect directly. For some components where you cannot do that, you can simulate those. And they will generate something which is called a trace file. And there are tools that will show you those trace files. So you can essentially export from the simulation the internal state and visualize that and inspect what's going on. And you can actually write proper tests with assertions and verify that things are working properly once you fix it to prevent regressions. The code that you'll find here that has no tests yet. I plan to add them, but I was testing manually at this point.
Any other questions? Everybody please give a huge round of applause for the speaker.